So this talk is basically going to be an attempt to give a whirlwind tour of what I think the most interesting things happening in the field are, what I think some of the most historically interesting results have been, and just kind of trying to give a general vibe of like, what even is Mechinterp, man? You can see the slides at this link, and I've got some couple of other links you might want to check out. I'll particularly highlight my guide for getting started in the field, and my MATS application, which goes live like yesterday, for people who want to get into doing mechanistic interpretability research. This is basically a program where I full-time mentor people for like 3 months in January of next year. And applications due August 30th. So if by the end of the talk you're like, this wasn't a complete waste of time and sounds mildly interesting, you should totally apply. All right, so what is mechanistic interpretability? What is this stuff? So the core hypothesis of the field is that neural networks are kind of, well, canonically, neural networks are incomprehensible garbage black boxes. But the hypothesis of Mechinterp is that they're not incomprehensible black boxes. We just don't know how to comprehend them. That there are human comprehensible algorithms inside, that there is a lot of rich interpretable structure, and that this can be understood if we put in the hard work to make it legible. And there is always this core tension between achieving rigorous understanding without tricking yourself, which is so easy to do. You can draw an analogy here between how you might take a compiled program binary and try to reverse engineer it to the source code, though that's very much the grandest and most ambitious form of Mechinterp. And I think there's many worthwhile things to aim for that fall short of true decompilation of GPT-4 into Python code, which kind of just doesn't really seem that tractable to me. And yeah, so beginning with just a whirlwind tour of what is a transformer, the type of neural network behind ChatGPT, Gemini, Claude, etc., for people who aren't familiar. The first thing you should always ask about a neural network is what is the input and what is the output? Because this is just how they're trained. They get an input, they produce an output. Yes?
I've often seen this analogy made with reverse engineering source code, like from the program binary. Do you have a sense of how successful people are at doing exactly that? My sense is that even that reverse engineering neural networks would be much harder than that, but even reverse engineering compiled code is very difficult. Is that matching with your sense of it?
So I'm not at all an expert. My understanding is that literally taking a binary, knowing nothing about it, and fully reverse engineering it to source code is incredibly hard. And that in practice, people have like lots of tricks and hooks into this. Like they really care about understanding a specific part of the program and can reverse engineer that. Or they know a lot about the libraries that were probably used and can leverage that knowledge and things like that. Regarding whether neural networks are like easier or harder, I think they're like different and hard to compare in a bunch of ways. If I had to say, I would say neural networks will be harder, but there's also, I don't know, I'll talk about tools like activation patching and sparse autoencoders, which are really helpful on neural networks that just don't at all make sense on discrete logical programs rather than things made of linear algebra, for example. And again, this is the aspirational goal. I don't actually expect us to get there, but I think that partial progress still could be extremely useful. Anyway, I'll generally be leaving like natural breaks every 10, 20 minutes for questions. So raise your hand if you think that something I've just said doesn't make sense in a way that is stopping you from following the talk. But for like more zoomed out questions, wait till the breaks. All right, input, output. Input of a transformer, sequences of words. Technically, a sequence of tokens, which are like words or word fragments, but if you think about it as sequences of words, you get basically the right intuitions. The output is a probability distribution over the next word. Importantly, every word in the sequence, the transformer takes in a sequence and it outputs a sequence. So what it actually does is output a sequence of probability distributions over each of the next words. So like, the first output is a guess for the second word. The second output is a guess for the third word, etc., which is often an unintuitive detail. The reason this isn't just complete nonsense is that internally the model is set up so information can only flow from a current word to future words, not to past words. So it can't just look at what the second word is to output what the second probability distribution should be. Internally, the central thing in the model is what's called a residual stream. It's like a sequence of representations, just vectors, one for each token. And there's one per layer. Modern models will often have like hundreds of layers. And the way to think about it is that each kind of layer or sublayer of the model is like an incremental update to the residual stream. It takes in the residual stream, it does some computation to produce a small diff that gets added to the residual stream, which is generally a fairly small fraction of what the model has done so far. So you can think of the residual stream as like the sum of all previous layers and like the accumulated knowledge of the model so far. Kind of a representation of the word plus context is often a useful intuition to have, though this sometimes breaks down. There's two types of sublayers. The first are attention layers. These move information between the different words. This is how you get and integrate the context. These are made up of what are called heads, which act independently and in parallel of each other. Often, but not always, we're trying to interpret individual attention heads and attribute roles to them. And the second type is MLP, which stands for multi-layered perceptron, which is the dumb jargon for the old-fashioned kind of neural network. These are for processing information once it has been moved to a word. And importantly, they don't move information between things, but they're where a lot of the network's like thinking takes place. And if you want to learn more about this, I have some YouTube tutorials, and one of the options in the tutorial later today will be going through a code GPT-4 from scratch notebook. All right, that's transformers. Any quick questions on that? Looks like, oh, there's a question.
Yeah, why is the MLP happening after adding up all the heads and not directly after the heads?
Because the residual stream is like all of what the model knows about the input so far. The attention adds to that, but you wouldn't want the MLP to only see the attention because that might have thrown away a lot of other important information. In general, when we find interpretable algorithms or circuits in these models, it tends not to be that like every one of the 200 sublayers matters. It's more like layer 5 matters and then it skips a bit, and then layer 10 is important and it skips a bit. So you really want the model to be able to kind of use the residual stream as much as possible, if that made sense. Cool. Question over there?
Sure. It seems to me, I don't know if I need the mic, I'll just start. Yes, it seems to me that, okay, now it's so close that So it seems to me that there's a common misconception that if a word or token tends to a previous token, for example, that means that that previous token has something to do with that word, or like it's important for that word. But sometimes I think instead it could just be moving the information of that word to this token because it might be used later. Is there any way of differentiating between those two?
Not that well. So you can kind of do hacks, like, so a really useful trick you can do is to say, the residual stream is the sum of every layer so far. When an attention head looks at a previous token and copies over some of its residual stream, that's a linear map. So you can also decompose that into what comes from each sublayer on that earlier token. And you can look at like which of these are important. Like if I remove everything but the attention layers that came from earlier tokens there, does it still work? And like that can give you some bits of evidence, but that wouldn't detect the case where an MLP layer kind of smushed together the earlier word information and the current word information, because it becomes very hard to tell the difference about where that's coming from. And I think there's like interesting approaches here, but yeah, this is not yet a solved problem, in my opinion. All right, that's it for transformer questions, but great questions. So I think that for many people in machine learning, they just kind of think that all interpretability is bullshit, because as is standard wisdom, machine learning is just stirring an enormous pile of data and linear algebra, throwing hundreds of $1 million of compute at it, and lo and behold, something magic happens. And honestly, I think this is like a really reasonable prayer to have. So I want to try to give an intuition for why I believe mechanistic understanding is possible, even in principle. And I'm going to be talking about this paper I wrote a few years ago on understanding how models do modular addition in the context of this phenomena called grokking. And spoiler, the algorithm is simple enough to fit on one slide. Why is one-layer transformers doing modular addition an interesting thing to study? Because of this phenomena called grokking. So grokking was discovered in this OpenAI paper. What they found is that if you take small models on simple algorithmic tasks, like addition mod 113, and you give them, say, 30% of the data to train on and 70% that it never sees to evaluate on, it will initially just memorize the training data. But if you keep training it again and again for a really long time, much longer than it took to memorize, it will seemingly suddenly grok and go from doesn't generalize at all to generalizes perfectly. And this is really fucking weird. Like, it's normal for a network to generalize. It's normal for it to memorize. But to do one and then switch to the other is very odd. And I was like, it's a tiny model. We could totally reverse engineer that. And I did. All right, so how did I get traction on this? So the first hint comes from looking at the embedding. The embedding is like the first layer of a transformer. And it's basically a massive lookup table that converts every token, everything in the model's vocabulary, to a learned vector, which don't necessarily have any relationship to each other, except what the model learns in training. And it turns out that if you apply standard dimensionality reduction techniques to the embedding here, where the tokens are just integers from 0 to 112, you get all kinds of like circliness. And this is the first hint there's something interesting going on, and that it involves trig and Fourier stuff. If you plot activations, there's also just obvious structure screaming at you. Here's the attention weight from head 0 from the final token to the first token, plotted across all pairs of inputs, or the first neuron plotted across all pairs of inputs. I did 0 just to illustrate that this is not cherry picking, it just all looks like this. There's clearly something going on here. And the key insight for unpacking what's happening is applying the Fourier transform. Specifically a discrete Fourier transform because it's a discrete vocabulary. And it turns out that if you do this to the embedding matrix and then take the norm, you end up with this incredibly sparse graph. It basically has learned to map each input to a linear combination of a few trigonometric terms, and the rest are just irrelevant. This is surprising because it means the model's only using about 12 of the 128 available dimensions for the embedding, which is kind of odd. And this is not true of normal models. Like at initialization, it just looks basically uniform because obviously there's nothing special about the Fourier basis to a randomly initialized matrix. And to cut a long story short, you can use this to actually decode the algorithm. The model has learned that modular addition is equivalent to composing rotations around the unit circle. In math jargon, these are isomorphic groups. The model learns that it can represent a rotation around the unit circle of a given angle in terms of sines and cosines of that angle. The embedding is a lookup table that just looks this up. It then composes the rotation, adding the angles using element-wise multiplication, i.e. the trig compound angle formulae. And then it does some slightly convoluted stuff at the end where it rotates backwards by each possible answer in parallel and then looks at the biggest one. And this is biggest when you're at 0, i.e. you rotated backwards by exactly a plus b. And it uses a softmax at the end as basically an argmax to just read it off. And don't worry if you didn't follow the exact details of that. The important thing is just there was a elegant, comprehensible algorithm. No one told the model to learn this algorithm. We just gave it data and said, go figure this shit out. But that we were able to reverse engineer it by just staring at the weights. I was expecting something much less galaxy brain to be going on. Though now I've said this for a while, I think it's actually a very intuitive way to do modular addition if you're made of linear algebra. How do we know this is what's going on? So we've got a couple of different lines of evidence. The first is just everything is ridiculously periodic. This is very surprising. The second is that you can just read certain stages of this algorithm off the model weights. Like some neurons learn frequency 14 trig features. And if you look at the weights from them to the logits, it just only involves frequency 14 terms, which is very surprising and not something you just see by accident. Neurons cluster into individual frequencies, and you can explain them with a simple polynomial of trig terms. A degree 6-dimensional term in a 12,000 dimensional space that achieves very good explanation. And finally, if we ablate the frequencies that we think matter, we significantly degrade performance, while if we ablate everything else, we actually slightly improve performance. Any questions on that so far? Yep. Loving the speed.
In the NLP, what activation function did you use? Did you use
ReLU.
Okay.
I expect it would be a somewhat similar algorithm without ReLU, but I don't remember if I actually checked.
So as you said, some specific neurons activate for very specific frequencies. And that seems to be very monosemantic, which can, I think, be expected from a small model. But maybe you are getting to this later. But how does this look like with far larger models that have to embed and array more complex tasks?
I will discuss that later.
All right.
But great question. Though I will say that I think it's a bit ambiguous whether these things are actually monosemantic or not, because they're not really learning like a one-dimensional feature. It's kind of a bit more like they're learning a two-dimensional circular manifold spread across like 100 neurons, and I don't really know what the right way to think about that is.
In a couple of the earlier talks that also touched on bucking, this clock and pizza thing came up at least a couple times. Can you comment on what your reaction to that follow-up work was in relation to the reverse engineering you did?
Sure. So the clock and the pizza paper was this cool paper last year that introduced, that was like, oh, turns out that sometimes if you mess with how exactly you're training this model, it learns a different algorithm for doing modular addition. Still clean, still interpretable, but like it's not always this like what they call the clock algorithm that I just explained. And I don't know, to me the key takeaway I want you to have from this section is just, it is possible to do reverse engineering on a system. I think there's a stronger claim that is sometimes made called universality, that there is like one algorithm that will be learned. And I think this is just pretty clearly false in the strongest sense that it's used. And the clock and pizza paper is like an empirical disproof of this. But I don't know, the main thing that I see as my job is take a big frontier model, maybe AGI one day, hopefully in the far future, and try to understand what the hell's going on inside. If there's multiple ways I could implement something, that's fine. I just need to make sure I'm being faithful to what's actually happening. I also think there's a big difference between, well, there's like 4 qualitatively different algorithms that could be being used for something, and there's like thousands, and we'll need to find the new ones every time, and any given model might be using all of the thousands at once. If the latter is true, that, I think, is much more of a mark against mechanistic interpretability than if we just need to learn like 3 rather than 1. And I think it's currently pretty ambiguous what's actually true in practice. An area of great future research, for the record. Does that roughly answer the question?
Thanks.
Cool. All right. Did someone already talk about like grokking and mechanistic interpretability?
I think there was a talk where your colleague talked about his work on grokking, but I don't know.
Cool. All right. I've got more interesting stuff later on, so I'll just skip this. Thanks, Vikram. And for anyone who didn't go to his talk, your loss. Should make better decisions in the future. All right. So yeah. Now we've got a bit more context. Let's return to this question of like, what actually is mechanistic interpretability? We want to reverse engineer neural networks. We have this hypothesis that they learn comprehensible algorithms and can be understood, but we have to make them legible. 2 key concepts for reasoning about models that we found seem to be empirically useful in practice are these ideas of features and circuits. Features are like variables inside a model. Like, this word represents a French noun or something. Or this is a variable name in Python code that refers to a dictionary, or something like that. These are stored in a model's activations. Circuits are like algorithms that are used to compute features, to use features to compute more complex ones, and to ultimately convert this into the output. And these are generally represented in the model's weights. And I think that there's this kind of fairly controversial question of how much detail we should be trying to go into in mechanistic interpretability, with some people being like, this is so uselessly bottom up and zoomed in, this is never going to go anywhere, you should just like look top down. And some people being like, I think all your results are bullshit, you should be going way more zoomed in and rigorous and like proof-based and working with tiny models. And I don't know, these are complicated questions. I kind of think about the ultimate goal of the field as something like forming an epistemic foundation for what a true science of interpretability could look like. I think it's really useful to be able to be rigorous and qualitative and like really understand what's going on in some specific situations, even if it doesn't generalize, because this can help us learn more general rules and build good and reliable techniques. But that if mechinterp gets to the point of actually being useful in practice for helping us understand and align human-level systems and beyond, it's plausible to me we'll be using stuff that's like much more zoomed out. But I think the best way to get to legitimate techniques like that is to just actually understand what is going on anywhere, ever. One particular motivation to me for this, though I think mechanistic interpretability is useful for alignment in quite a wide range of ways, is that I just think that it's really important to be able to understand a model's cognition. In particular, is it aligned or telling us what we want to hear? Like, what can we learn that distinguishes two model algorithms that look the same according to their behavior, but have very different things going on internally? And people may have seen this iconic part of the GPT-4 paper, where some people at Meta, formerly ArcEvals, were trying to get GPT-4 to get a TaskRabbit worker to solve a CAPTCHA for it. The model instrumentally realized that it would be useful to lie all on its own, and then came up with a convincing lie that it had a vision impairment in order to get the TaskRabbit worker to do what it wanted. And I'm not scared of GPT-4. In particular here, it literally had a scratch pad we could read. But I think this makes it pretty obvious that we'll soon be in a world where we have systems that are just capable of spontaneously deciding to lie to us in ways that are reasonably convincing. And I want to be able to tell the difference. And in particular, it seems pretty plausible to me that we'll end up in a world where we have an AGI, it seems aligned, and we need to figure out whether we can deploy this into the world. And I don't think that it is a realistic answer to just say, we will never deploy AGI and hope we can just coordinate the world to like forever leave behind this incredibly valuable technology. Maybe I'm wrong on that. I'm down for people to go investigate that path, but I'm skeptical. And so we need to have some answer, some safety case. And I think interpretability is like pretty far from the level of reliability where I actually would back it to be that safety case. But I think it has the potential to get there, and not many things have the potential to get there. And yeah, I would be very excited to see people trying to actually push on this, both just doing basic science to push forward the field of interpretability and looking at how we can actually decode the cognition in models in practice. On a more personal note of why I like doing mechanistic interpretability, I think it's unusually easy to get started and get good feedback loops compared to most of machine learning, and especially most of alignment, which is just, fun. To me, it feels like a kind of cross between the part of my mind that likes thinking about maths and linear algebra and algorithms and computer science, and the part of me that just like deeply cares about truth-seeking and empiricism and designing good experiments and trying to like find true things from the morass of vague hypotheses in the world. And for anyone here who has been trying to get into the field or is thinking about this, I think a crucial bit of advice is Mechinterp is a empirical field, not just a theoretical one. You want to code early, you want to code a lot. You want to challenge your preconceptions by actually testing your hypotheses and getting in contact with reality. And one of the most common mistakes I see is that people are just insufficiently skeptical. They come up with a beautiful hypothesis that they get really attached to, and they lack the deep-seated cynicism required to aggressively try to break it. And often, your beautiful hypotheses are wrong, and this is sad. And a question I often get in alignment circles is, sure seems like a lot of people think Mechinterp is sexy and want to get into it. I, as a glorious hipster who cares about neglectedness, think this means I shouldn't do it. What is your advice? I think that my general take here is that personal fit and intellectual curiosity and draw to different fields massively affects how much impact you can have and how good your research will be. And first and foremost, you should be optimizing for like being the best researcher you can in any fields. But that if you don't feel any particular draw to mech-interp, or there's other stuff you feel comparably drawn to, neglectedness should be a nudge towards pursuing those other things. But I don't know, different people vary on this one. And you can check out my Getting Started guide or my tutorial later on for like practice getting your hands dirty a bit. And yep, some more stuff that I mentioned at the start. I will replug my maths program, and there's also a bunch of organizations you might want to apply to for jobs, though I don't know whether I still endorse the OpenAI Mechanistic interpretability team given recent events. So I should probably remove that one. All right, so next section. Any questions on what's been covered so far? Yep. I can hear you, but you've almost got it.
Just a question on what you should ask afterwards, I think, like what domains you find useful to know to make progress in the skills.
Mm-hmm.
For example, you use Fourier transform. Okay, you need to know what a Fourier transform is to identify in the model. So in that sense, like and more specifically, like when you've got knowledge of and reasoning and classical symbolic AI, what domains such as that be useful in trying to identify progress in the skills?
So I think there's two subtly different questions that people often ask like that. There's, I have knowledge in field X. Will this give me an edge in mechanistic interpretability? And I do not have knowledge in field X, but maybe kind of want to learn it. But really, I want to do mechanistic interpretability. Is this a good use of time? And lots of fields fit into the first category of like, yeah, they're probably useful. Not many fields fall into the second category of like, they are a good use of, they are like the optimal use of time to learn if you're trying to get into the field. Like, the best way to get into mechanistic interpretability is just to like, go and learn about mechanistic interpretability. Read some papers, do some coding tutorials, code your own transformer from scratch. And I think if I had to pick some fields that I do think are like really valuable prerequisites, it would be kind of fluency in linear algebra. Things like just being able to very comfortably say, oh, I'm going to take a singular value decomposition here, and like I just know what that is. Or, oh yeah, transformers, they're basically linear. You can multiply together these four matrices to get an effective linear map. And I can kind of reason about what that might do. This looks much more like practice a bunch of linear algebra problems and like read papers and try to follow them than it does like learn a bunch of theorems, in my opinion. The second would be fluency with PyTorch or some other ML framework, though I recommend PyTorch for mech-interp, and fluency with like what is a transformer. Yeah, I don't think classic AI and symbolic stuff is like particularly useful. I think it's very plausible to me that, say, neuroscience or cellular biology or other fields that kind of look at systems that have come out of a weird optimization process and try to reverse engineer them have insights that have not yet penetrated the field of mech-interp. And if anyone here has a background in those fields, I'd like be super down to chat. And I generally am like always excited when I see someone with a background like that who's just already invested it. But if someone was like, should I go to a PhD in neuroscience? I'd be like, no, just like go learn mech-interp. So not worth 6 years of your life. No offense for any neuroscience PhDs in the room. All right, any other questions?
One question is, with interpretability, a lot of the different papers seem to be focusing on like kind of different tasks and have like different ways of evaluating how good the interpretability succeeded and so on. What do you think of the concept of creating interpretability benchmarks or similar? Do you think that's a sensible thing to do, and what might that look like?
So Many people have tried this. I don't like any of them, I think, though I haven't read all of the papers, so maybe there's some that are like actually good. Let's see. There was, well, I'm currently thinking of examples that are on my reading list that I haven't actually read yet, but there was a recent paper called Ravel from Atticus Geiger's group. There was like a disentanglement benchmark. There was one from my math scholars, Alex Makalov and Georg Lang, on like evaluating sparse autoencoders, which I actually did really like, though I'm massively biased. I think Morgava has put out a few. Like there was one on ripple edits. Like if you edit part of a model's knowledge, does it propagate to like consequences of that knowledge? Though I kind of think all of that is just doomed. There was, those are the ones coming to mind. I'm sure there's more. If you check out related work of these, they'll often have more stuff. Oh, I think there was one called like Interpbench from Ivan Morena and Rohan Gupta. There was a poster at my ICML Mechinterp workshop. Anyway, yeah, I guess I'm broadly like, well, it really sucks that we don't know how to measure things, but it's not because no one has sat down and put in the effort to just make a benchmark and it's just a bunch of legwork. It's like a deeper issue that this is a pre-paradigmatic field, and finding the right measurements that actually capture what we care about rather than being weirdly good-heartable summary statistics is like a big open research problem. And I'm very excited about people working on those. And I think that there are examples of papers that have just done quite good measurements. But I don't know. I think that trying to make a benchmark from it without first coming up with a thing that I actually feel comfortable trusting is putting the cart before the horse a bit. Though making the benchmark is often a good way to get empirical data on how much I trust it. But yes, it is very annoying. If someone wants to fix this, please be my guest. All right, next section, sparse autoencoders and superposition. How do models represent their thoughts? This is very much a how do features work section. So a core goal in mechanistic interpretability is to decompose models into independently meaningful and composable units or features. These are things you can analyze in isolation without needing to understand the rest of the model. And composable meaning you can interpret circuits in terms of how they all fit together. Models are fucking enormous, so this is a big deal. Note that what I'm talking about right now is decomposing activations, not decomposing parameters. Typically, a model like GPT-3 will have hundreds of billions of parameters, but the activations will consist of like 100 10,000 dimensional vectors or something. So painful, but like less painful. Where a canonical example of an activation would be like a residual stream activation or MLP hidden layer activations. A hope in the early field was that neurons, i.e. basis elements, kind of the basis directions of activations, especially in MLP hidden layers, would be features. They would be interpretable, it would be beautiful. Sadly, there's this problem of polysemanticity, aka our beautifully optimistic hope is just kind of bullshit. For example, here's a neuron in CLIP, which seems to activate on like poker and card games and poetry. Which, you know, is possibly a PO feature, but broadly just seems kind of garbage to me. And like, this wasn't a naive hope. Like, people often have the reaction of, but it's just a vector space. Why would any basis be more interesting than any other basis? But there is often something special about the standard basis in these models. Like, we have element-wise activation functions, like relus or gelus or geglus. And these kind of act independently on each basis element, meaning that you can allow them to vary independently of each other. But if you rotate, suddenly each one is entangled with everything else and it's a clusterfuck. So this was like a reasonable hope, but it just doesn't really work that well. Our hypothesis for what's going on is that models are using this phenomena called superposition. The idea of superposition is that it's actually possible to represent more features as directions in space than you have dimensions or neurons. This is compressed in the sense of you can't just perfectly extract the coefficients of like 1,000 dimensions from a 500-dimensional space because linear algebra facts. But you can do this in a kind of lossy way. And you just have interference between features that are not orthogonal to each other. But it turns out that this seems to be used quite heavily in practice, as far as we can tell. Evidence base for everything in Mechinterp is like a little bit sketchy. And what we think is going on is just it's more useful to represent more features. And it's worth tolerating the interference. And it would be kind of surprising if the optimal amount of interference was literally 0. One of my all-time favorite papers is Toy Models of Superposition from Anthropic, which works with well-chosen toy models to try to simulate how contexts where superposition makes sense. And what they find is that if you train a toy autoencoder, that is a model that has a space where, let's say, 5 dimensions, each one varies independently, maps it down to a 2-dimensional space linearly, maps it back up, no activation function in the middle, and you try to interpret, and then you try to look at what happens in the middle. Initially, it just represents 2 features orthogonally and throws everything away. But if you start to make the features sparser, i.e. make most features 0 with high probability, then it starts to compress things. It starts to squash more things into the middle than it has dimensions. And you get these beautiful antipodal pairs or pentagons showing up. The key idea for why sparsity matters is that superposition is a trade-off between the benefits of representing more things and the costs of interference. But the most damaging kind of interference comes when 2 features that are not orthogonal both occur at the same time. If a feature occurs with probability p, the 2 independent features co-occur with probability p squared, while the benefit of storing a feature scales with probability p. So as p gets smaller, going from 100% to 10%, superposition becomes a better and better deal, and models are willing to tolerate more interference. The kind of underlying hypothesis behind everything I've been saying so far is what's called the linear representation hypothesis, which is that a model's activations are sparse linear combinations of meaningful feature vectors. What this means is that there's a big dictionary of features the model knows about, and a big dictionary of features the model knows about, and each has a vector associated with it. And on any given token, the model chooses some sparse set of these, e.g. the I'm in Paris feature is just not relevant for most things. Likewise, for basically any feature you can think of, apart from maybe I begin with a space or something. And we then just add up the vectors for this sparse set of coefficients, weighted by how relevant they are to the input, how much they fire. Here are some cute graphs from the classic word-to-vec paper, which found a vaguely similar thing in word embedding models. Like there's a royalty direction and a gender direction. So you kind of get that queen to king is woman to man. Though please take this as an illustrative example because that paper was kind of sketchy. Question? But yeah, this is a pause point for questions in general, if anyone else has them.
Regarding the previous slide and the nodes moving towards zero, is this an effect of weight decay, or does it happen with any gradient descent method?
Ooh, sorry, what?
You said certain nodes are moving towards zero while learning features. Does this happen only when I apply weight decay, or does it happen in stochastic gradient descent no matter what the exact descent?
Are you referring to the fact that in the 0% sparsity one, 3 of the features are mapped exactly to 0?
Exactly, yeah.
That's nothing to do with weight decay. I think they might have used it. I don't think it matters. The main thing is that's just incentivized by performing well on the loss function. Like, if they don't map to 0, they cause interference. Also, we're approximating. It's not literally 0, because getting to literally 0 is really hard, but it's close enough. Yep.
Can you please explain what feature importance means in this diagram? Or like what is plotted?
It's intended to be a proxy for how much a feature reduces loss in natural language. This is a toy algorithmic model, so the way they do that is they just literally assign a coefficient to the mean squared error of that feature and just add them up, and they just have some like decaying schedule. Sorry, they just go from like big importance for the first feature to small importance for the second feature, which kind of gets the model to prioritize, like, I'll learn these 2 features and not learn the 3 unimportant ones. I wouldn't obsess too much about the detail. The key thing is just like, we think that features vary in how much the model gives a fuck about learning them, and that's reflected in how high priority they are to learn.
Thank you.
I don't see any other questions, so I will either assume I'm being incredibly clear or so unclear you don't know what to ask. All right, so what do we do? The solution we currently maybe kind of think is this technique called sparse autoencoders. The idea is that we train a autoencoder to reconstruct the activations. An autoencoder is just a thing that maps the input to itself to try to reconstruct it, with some constraints on the middle of the autoencoder to make that a more interesting representation. Typically, you make the middle of an autoencoder smaller because this kind of makes it compress the model. But here we want to make it decompress the model. So the gimmick we use is that we make the hidden states sparse. We take the sum of how good is the reconstruction in terms of mean squared error, and what is the sum of the internal activations, which encourages it to have as many of those be 0 as possible. We used relo activations, so they're always non-negative. And the hope is that, so the sparse autoencoder should learn a sparse reconstruction. We don't know how to directly optimize it to be interpretable, but we believe that there is an interpretable sparse reconstruction, the like actual dictionary of the model's features, if there is a meaningful ground truth there. And what we think is that, if we do this, then the best sparse reconstruction, the one the model learns, will also be the interpretable one. And that we can get interpretability kind of for free by instead optimizing for this much easier proxy of sparsity. The actual architecture of our SAE is a very simple two-layer classic neural network. Technically, it's a dense neural network, but I think it's very confusing to call a sparse autoencoder dense. It's kind of doing these two different tasks. We want each neuron in the sparse autoencoder, or each latent, to be an interpretable feature, which means we want its decoder vector to be the meaningful feature vector for that, and the activation of that latent to be how much that feature fires, and like, does that feature fire? So the encoder is a matrix multiply followed by a ReLU that tries to find this sparse vector of coefficients. The decoder matrix tries to just be that massive dictionary of features. And Anthropic did some fantastic work in this paper towards monosemanticity, which I apparently forgot to put a reference to on this slide, showing that they basically work in one-layer language models. Here's an example of the Arabic feature. This is a histogram of how much the feature fires, and the y-axis is how commonly it fired, and the shading is like, was this Arabic text or not Arabic text, which is quite easy to analyze by just looking at the characters. And a crucial thing that I want to highlight is that sparse autoencoders are an unsupervised method. We don't tell them, go look for things like Arabic features. We just tell them, please go and figure out a good sparse decomposition. This is a double-edged sword. It means that we don't know what the features mean by default. We have to label it as an Arabic feature by doing things like looking at the text that makes it activate a lot, or having an LLM do that for us, and looking for patterns. But it also means that we aren't imposing our preconceptions onto the model of what features it should be learning. Instead, we have a real shot at actually finding what it thinks it ought to have learned. Like, what is the best way of decomposing the model? And I think this is really important because it's really easy to impose false preconceptions onto a model, because models are weird, fucked up things. And often what's intuitive for us is not what's intuitive for them. For example, doing modular addition with Fourier transforms. And I think that especially as models get more powerful, the way they choose to represent a concept, like deception or manipulation, might start to get weirder and not exactly what we think we ought to be looking for. In follow-up work, both Leo Gao at OpenAI and Adley Templeton and co. at Anthropic scaled these up to frontier models, respectively GPT-4 and Claude Medium 3, or Sonnet, but Sonnet 3, not Sonnet 3.5, and found that they just keep working. They have become a much grander engineering pain in the ass, but they find weird interpretable things. Like, I don't actually know how readable. It's reasonably readable. But they found a bunch of weird, abstract, and multimodal features. My personal favorite from the Anthropic paper is the unsafe code feature, which activates on unsafe code, but also activates on the picture, do you want to turn off safe browsing? Or, this website is unsafe, are you sure you want to proceed? Which is just like, what? It's fucking wild. And I highly recommend just reading all of the beautiful examples in that paper. You can also steer with features. They're causally relevant. You can do things like turn them on, and now the model will obsess over this feature, or turn it off, and now the model will just forget about this feature, or even set it to a big negative value to suppress it. I'm sure many people here have seen the absolute iconic meme of Golden Gate Claude at the top, where you get it obsessed with the Golden Gate Bridge, ask about its physical form, and it tells you that it is the iconic form of the majestic bridge itself. And we had a fun hackathon at DeepMind replicating this paper and also showing that you could convince Gemini it's a goose with a steering vector made from 6 prompt pairs. And I think this is important because sparse autoencoders are still quite an early stage technique, and it's possible they're just doing things like clustering the data in some way and giving you, and you find like a data cluster and it looks interpretable, but just like if you just took a residual stream direction and then looked at the things which were smallest Euclidean distance from that, that's probably pretty interpretable because space is big. And I think finding causally relevant features which also don't break the model is exciting to me as like stronger evidence that we've actually understood something about the model's internal computational basis. Just check, I have till 20 past?
You have still lots of time.
Cool. When does this end?
3:30.
Oh, cool. All right.
No, like 20 past 3, so it's 15 minutes.
Cool, 15 minutes, great. You can also just use sparse autoencoders to actually do cool things in models, like find circuits. I really liked this paper from Sam Marks called Sparse Feature Circuits, where they basically took existing techniques for finding circuits in like the neuron or attention head basis and adapted it to work with sparse autoencoder features, which, being much more interpretable, are like a much more natural thing to work with. And the coolest result is they were able to take a probe that they trained to classify professions of like LinkedIn bios with a spurious correlation where they detected the gender and used the gender to predict someone's profession. We're able to delete gender-related SAE features and significantly improve the probe's ability to correctly classify like male nurses as nurses and female professors as professors. I'm not claiming this is real-world useful in any way, shape, or form, but I think that achieving real results that are difficult to achieve in other ways is a really important thing that I want to see more work on in mechanistic interpretability, because it's one of the best ways to keep the field honest that we're actually learning real things. And yeah, I forgot to put animations on the slide, so sorry for the wall of text. But I think that sparse autoencoders are like the most exciting and interesting frontier in mechanistic interpretability right now, and that there's just a ton of cool open problems to get at. For people taking pictures or notes, reminder, you can see my slides at neelnanda.io/whirlwind-slides. A couple of examples of problems I'd be particularly keen to see work on. Just how do we make better SAEs? There have been papers like gated SAEs from my team, Top K from OpenAI. We're about to put out a paper on jump relu SAEs, which seem to be narrowly SOTA. How can we get better reconstruction? How can we get more interpretable SAEs? How can we train them faster? They are like a pretty irritating engineering challenge to train, especially on frontier models. And we just want to get the best bang for our buck that we can. How do we do this? How do we measure the performance of an SAE? How do we evaluate it? Like, we can look at things like, is it good at reconstructing at a given level of sparsity? That's quite easy to compute. But what we actually care about is, what can we do with them? Can we measure how useful it is on a real-world task? Can we measure how good it is for finding circuits? Can we measure how good it is as an interpretability tool? We have proxies, but are the proxies any good? We just don't really know. And I think this is like a massive bottleneck on our ability to iterate on training better SAEs and to figure out which of the many techniques out there we should use. I'd love to see more work on scalably finding SAE circuits. Like, there's just a lot we don't know about what's going on inside models. SAEs seem like they've really unlocked our ability to understand transformer MLP layers. And I think there's a lot to learn on that front. better techniques for circuit finding, doing it faster, doing it better, measuring how good they are, understanding whether the SAE base is even the right place to look, applying SAEs to real-world tasks. Can we detect hallucinations or jailbreaks? Can we find natural adversarial examples better by using the SAE to guide your red teaming and exploration? Can we take weird behaviors in open source models that we just don't understand and debug them? Like, I would love to get to the point that the next time you get a bizarre scandal like Bing Chat gaslighting users, the obvious tool to reach for is an SAE to try to debug what was going wrong and how this could have been fixed. If you're here and you're like, SAEs, they seem kind of overhyped, I would love to have more people red teaming them. Are they doing what we think they're doing? They introduce error. They don't perfectly reconstruct things. Can we interpret these? What do they mean? How big a deal is this? How big does our SAE need to be before the error term can be safely ignored? One concrete opportunity here is these are all much easier to work on if you already have high-quality trained SAEs. So in a few weeks, my team's going to be releasing several hundred SAEs on every layer and sublayer of some Gemma 2 models. And we're going to be opening this for early access like either tomorrow or Monday. So DM me if you have a project you're keen on working on that would benefit from these. And if you want to just like play with SAEs and the kind of weird shit you can find inside models or try steering with them or anything like that, neuronpedia.org is a fantastic website. All right, I do not have that long left. I think the most interesting thing is explaining what activation patching is and then taking questions. So activation patching is one of the key techniques for doing principled causal interventions on models, especially but not limited to using it for circuit finding. This is also known by many other names, such as causal tracing, causal mediation analysis, resample ablations, interchange interventions, because we as a field are deeply incompetent and cannot agree on a name. And so what's the idea of activation patching? I've got a prompt, like the Big Bang Theory premieres on, and the answer is CBS. And I want to understand how the model knows this. And the standard technique is an ablation. You just like take a bit of the model, you set it to 0, you see what happens. If it breaks, you're like, that was clearly important. But this is too crude a tool, in my opinion, for telling where the knowledge is stored. Because you might have just broken the speak English bit, or the token passing bit that's important for recognizing any multi-word phrase as a single entity, or the I should be doing factual recall right now bit. And there's just like lots of parts. The key idea of activation patching is to set up what's called a contrast pair. Another prompt that is as close to the first one as possible, but different in some key detail. Like Brooklyn Nine-Nine premieres on, or Game of Thrones premieres on, or something. And now you can patch things from the theory token into the Thrones token, and i.e. just take an activation, like the residual stream at layer 17, on the theory token, patch that into the Thrones token, overwriting its residual stream at layer 17, and then see if it now says CBS rather than HBO. Or you could patch the Thrones one into the Big Bang Theory one and see if it breaks its ability to say CBS. Kind of test, one tests for if you found an activation that's sufficient for the right answer, the other tests for if you found an activation that's necessary for the right answer. And this is just like a really, in my opinion, very elegant, but also incredibly important and useful technique. Because if you just carefully set up your contrast pair to differ in some key information, e.g. changing premieres on to the Big Bang Theory was directed by, to isolate the bit of the model that handles what the factual relationship is or something. you can really start to decode the key bits of what's going on. And yeah, so skipping ahead. Yeah, so here are some links if you want to learn more. I would particularly recommend the Arena coding tutorials and my Getting Started guide. You can see my slides at that link. If this has got any of you interested in Mechanistic, I would love your applications to my Mats program at tinyurl.com/Neel-Mats-app. And yeah, I'll be doing a tutorial later today where basically I'll be having you go through a new sparse autoencoder tutorial. It's not one of the Arena tutorials, though this does mean it is much more likely to have bugs. And but you'll also have the option to go through some other Mechanistic tutorials, depending on what you want to learn, e.g. one on how to code your own transformer, if you're just totally new to the space, or one on activation patching and circuit finding, depending on what you're interested in learning. And I'll kind of like give some context and framing at the start, and then circulate and be available for answering questions. And you're welcome to come to today's, tomorrow's, or both. And if anyone here feels comfortable with Mechanistic and wants to also come and help answer people's questions, that would be appreciated, because if I get anything like the number of people in here, I am not going to be able to keep up. But yeah, happy to take questions in the last 5 minutes.
So thanks for the intro. We have time for like 5 minute questions.
Yeah, a question about sparse autoencoders and kind of the hope for getting interpretable features out of them. Like, we know from adversarial examples that there are, like, for image classifiers, adversarial examples which generalize across networks. So somehow, maybe they're learning like a feature that is not human interpretable, or not obviously human interpretable. What are your hopes, like, as we scale frontier models, that the features learned will actually be human interpretable?
Let's see. So I'm kind of confused about what the state of the literature is on universal adversarial examples for language models. Like, there have been some papers on it, but I think they were like significantly overstating their results and got like partially debunked by follow-up work, though it does seem like they achieved some amount of generality. It definitely seems like this was a real thing in images, though my understanding, based on the adversarial examples of features not bugs paper, is that it's more like they're kind of learning some low-level texture things that isn't perceptible to us but is a real feature. And for that, I'm just like, that's great. That's a real feature. I want my SE to learn that. And maybe we'll need to get better techniques for identifying that kind of cluster of feature. But like, if something is universal across models, which is not that hard to test for, even if you don't know what it means, and we can kind of understand the context where it's causally relevant and like the kinds of places it occurs, I feel like you could get some understanding from that. I think a pretty cool project would be taking something like an adversarial suffix made from a technique like Andy Zou's GCG on a model which has a sparse autoencoder trained on it, and then just try to understand what's going on. E.g., can the SAE preserve the adversarial example behavior? And if so, what does that look like in terms of the features? Versus, is it that it's exploiting some weird part of the model's latent space that the model has never seen in the like SAE training data or something? I don't really know. I think that it's certainly possible you get weird alien abstractions, but I'm not really convinced there'd be kind of truly alien abstractions that are beyond our ability to understand. I just expect there to be more, unless, I don't know, we're talking about some like godlike superintelligence that's on the equivalent of mentally rederiving quantum mechanics. But even then, like, That's not incomprehensible, that's just hard, and we need to up our game. But I do think that there's things that a human cannot interpret in 2 minutes is very likely to happen and has totally already happened. Yeah. Jesse?
So if we take seriously the premise that in-context learning is learning meta optimization, right? Maybe it's doing SGD in context or some Bayesian inference in context.
I don't take that seriously, but as you were.
That's the answer why you don't expect uninterpretable features. But then my actual answer, my actual question is, why don't you expect that at all?
Sorry?
Why don't you expect that?
I don't know, I'm just like, it seems like everyone who's been doing this has been using super toy models, and I'm like, sure, you can learn an algorithm in an algorithmic setting that kind of looks a little bit like SGD if you squint, but those papers just seem super overhyped to me, and I haven't come across anything that seemed like evidence of this happening in language models. I have not deeply engaged with this literature, so this is very much, well, this is my prior, there's a lot of papers, I have a very long reading list, I haven't prioritized this stuff, rather than I'm highly confident this is false. But that's kind of where I'm coming from.
So if I make a prediction of new qualitatively new abilities in the next generation of language models, it might be this. Or are there any other capabilities that come to mind?
It seems really hard to tell the difference between in-context learning that has learned a genuinely new thing versus a algorithm the model just had in its weights that got made more prominent by in-context learning. And I'm just not really aware of stuff language models can do where I'm like, I do not believe that it just learned that during training, or it learned a kind of abstract enough algorithm that this is a special case of that during training, that it just wasn't using until you hit it with few-shot learning a bunch. I totally buy that in-context learning massively upweights things and overrides other stuff. For example, many-shot jailbreak seems like a clear example of that. But I feel like people just think that few-shot learning is magic in a way that I don't feel is at all justified by the literature. Yeah.
Okay, so thank you for an interesting talk. So I'm not a technical guy, I'm a philosopher, so I'm going to give you a question completely out of left field if you don't mind.
Go for it.
But with my colleague, right, we have been looking at this problem of interpretability of AI from this epistemological perspective, and you had dealt that what you want to do is, build some epistemic sort of framework to understand these AI. So I would like to add the question that we are looking into exactly like the question of what makes something understandable to like human beings from like the epistemological or psychological perspective. And we sort of arrived at that in epistemology we identify different kinds of questions. For interpretability, two important questions came up. Is that sometimes we answer the questions in like the how way, or we answer the how question, which sort of like determines the set of causes that are removed will prevent the event from happening. And when we look at interpretability, to us it seems like, yeah, this is the sort of explanations you generate. You look at some features, you identify this feature led to the particular output, or this feature this activates particular nuance and so on and so forth. But we found that to make to relate the model or something understanding to humans want to have a why question answer. And why question is more contrasted, in the sense that people want to explain not the event per se, but explain the cause of an event related to some other event that did not occur. Right, so for example, I think in your you have something similar like this. When you like talk like when the AI is doing some calculations or something, you thought, it was doing this algorithm I did not at all expect. Right? And this is this sort of element of surprise that causes us to ask questions that we sort of won't answer. So what I would like to ask you is, how do you think that mechanistic interpretability can try to answer these kinds of questions? Where you sort of need to like create this contrast to make, sure, you can identify some algorithm in the model, but you could ask yourself, but why is AI executing this particular algorithm except for a different?
Yeah, so I guess I personally consider that a, also, do you want to pass the microphone to the guy over there who had a question? Yeah, you. Yeah, so I guess I say the main job of Mechinterp as taking a neural network with a bunch of algorithms and explaining what those algorithms are. It sounds like you're asking about the question of why did it learn this algorithm rather than another algorithm, which, I don't know, I feel like is more a question of like, what was in the training data? What was useful for getting good performance in training? And there's techniques like influence functions. There was a very nice Anthropic paper from Roger Gross on that, which are like, which training data was useful for this? Which feel like more the right tool there. Like, I'm sure Mechinterp could give you some insights, but it's not real. That's not the question I see it as my job to answer, if that makes sense. But yeah, question over there?
Yeah, thanks for your talk, Neel. So I'm not super familiar with sparse autoencoders, but from what I understood, you were describing before that when you want to figure out the semantics of a feature that you found, you kind of have to show it some text and figure out when is this feature getting activated or highlighted. What does it highlight? And that seems like, let's take the erratic text feature, for example. If I imagine that I don't know that it activates that, I'm just trying to sample a lot of text from my training data, I might have to sample really a lot before I find the specific text that it activates on. Is there a smarter way to do that? Maybe you could even reverse it and try to turn up the feature and generate text, and then it might generate erratic and you then know. Or, yeah.
So I actually, two of my math scholars, Stepan and Dimitri, actually have a post coming out that's like essentially that idea in like a week or two. Essentially, you ask the model, what does X mean? You replace the residual stream on the token X with the SAE feature times 100 or something, and then it generates text. And this works surprisingly well. I'm not convinced it's as good as get max activating examples and then have GPT-4 explain them. And it does require your model to be smarter than, say, GPT-2 small. But say Gemma 1 2B has seemed sufficient. But generally, I just think that like we suck at automatic interpretation of features. And I would be very keen to see people innovating on this.
Right, and get max activating samples would require that you sample a lot, which means that perhaps the features that you end up finding, maybe there's some very, very unique features that you never find because that would require sampling so much that it's like a much more unique kind of things going.
Maybe. You can do the sampling once for all features, so it's not that bad, but it's still irritating. Anyway, I think we should probably wrap up there. I'm happy to hang around at the front if people want to come up and ask questions.
Yeah, so
Thanks so much.